In this section, we're looking at graphing the different energies, and the key really is the fact that K, the kinetic energy, is never a negative quantity. We can see this for the relativistic kinetic energy, because K is equal to gamma minus 1 mc squared. Gamma is greater than or equal to 1, which means that gamma minus 1 is always going to be 0 or larger. If we look at the low speed approximation, we have that K is 1/2 m v squared, and whether or not v is positive or negative, v squared will always be a positive value. So the kinetic energy of a system can never be negative. So if we go ahead and we plot all of the energies on the y-axis versus the separation between two particles or whatever, and let's look at an attractive potential. Let's look at the case of, say, a gravitational attractive potential or a positive and negative charge. They're all going to have the same shape to their potential energy, U. It's going to look something like that. So if we go ahead and let's start off with a negative total energy. All right, the total energy can be negative. It's only the kinetic energy that has to be positive. So, and let's take the case where the total energy is constant, a constant negative value. So if we plot this on this graph, it's just going to be a horizontal line. Total energy is the same everywhere. Now, if we want to figure out what the kinetic energy looks like, what we can do is, let's take a look at this point right here where total and potential energy are the same. Now, the relationship between the different energies is that E total is K plus U, or turning that around to solve for K. K is equal to the total energy minus the potential. So at this point right here, where the total and potential energy are the same, the kinetic energy is going to have to be 0. This point right here is called the turning point, and this is the point where an object that would be moving, say, in an orbit or whatever, would turn around. Now, if we look at a point over here, we see that the potential has a more positive or less negative value, and so the difference between these two will actually be a negative number. What that means is it's not possible to have a kinetic energy for any of these regions here. So this region is essentially considered the forbidden region. We can't have any particle motion in this region of space. It is forbidden by the fact that the kinetic energy has to be positive. Now, if we take a look at E minus U at, say, this point, well, the kinetic energy will be a positive value with a magnitude equal to the height of this bar right here, E minus U. So that's going to be, say, right about there. If we look at E minus U at this point, we can see that the kinetic energy is going to be larger. And if we look at this point right here, it's going to be even larger still. So the kinetic energy will look something like this, where it goes to infinity as r goes to 0. So an object that's moving, and let's take the example of an object that starts on the surface of the Earth and is launched upward. Let's say it's a ball that's launched from a rocket, or from a launcher that's shot straight up and goes back down. So that would start at some height with some velocity, and if the velocity is too small, if the initial kinetic energy is, the initial total energy is negative, what will happen is this ball will go up to a certain height, and when it reaches this point right here, where the total and potential energy are the same, the ball will turn around and fall back down to the surface of the Earth. So this point right here corresponds to this point right here, that turning point. Now, if we take a look at the case where we say have a positive total energy, I go ahead and redraw this. Energy is on the y-axis, radius or separation between the two particles is on the x-axis. And let's use the same type of potential, gravitational potential energy or whatever. This is our u, and now our total energy is a positive constant value. So we've chosen our system so that everything is inside the system, and we have a potential energy associated with gravitational attraction. And remember again, then we have that ET minus U is equal to the potential. Now let's try to figure out what that potential energy curve is going to look like. Oops, I want black. All right. So the potential energy is just equal to the distance between E and U. So when we get out here, U essentially goes to 0. That's one of the properties of the potential, is that as R goes to infinity, U goes to 0. And so our kinetic energy is going to get very close to E. Now, as we get in here, we can see that this distance between E and U, between these two graphs, is going to start to increase, which means that the kinetic energy is also going to start to increase. And when we get to this point right here, it's going to start to be pretty large. So this thing is going to speed up as it goes in. So the thing to notice here is that we don't have a turning point anymore. When the energy is positive, we no longer have that place where the particle is forbidden to move. One thing to take a look at is the idea of bound states versus unbound states versus trapped states. This really gives you an idea of the limits on the possible motions. That's really what this section about, is focusing on the idea of where the particle can and can't move and how it's going to be moving when it gets to those points. Notice that the kinetic energy doesn't really tell us the direction of the velocity. It only gives us information about the speed, the magnitude of the velocity.